Okay, so yesterday we started chapter 10 and did 10.1 talking about parametric equations and 10.2, which was in calculus with them. Now we're going to move on to the second half of chapter 10 that we're doing today at least. Chapter 10 does have section 10.5 and 10.6, which you cover 10.5 and 171 for those who've taken that. 10.6 gets skipped, I guess. So I feel bad, you don't feel bad for it, but that's okay. In any case, though, we're going to be doing polar coordinates, which again, if you've taken 171, you would have encountered this section, but not the calculus part. So we're going to be doing that. But first, we want to introduce the concept here, right? Just for those who hadn't taken the class. So polar coordinates. So first, I have a definition here for a polar coordinate system, just in general, where you have a graph where the points on this graph are represented by the distance there from a given pole, right? So in our case, our pole is just going to be the origin. We're going to just take like a typical kind of Cartesian system and just use the origin as our pole, right? And that distance there from that pole, we're going to represent by r. We're going to kind of call it like the radius, essentially the distance. Like you see, this point here is the distance r from our pole. So that's one part of the coordinate, and then the angle they are at compared to a given polar axis, right? So then you're going to be given from that pole, you're going to be given a certain polar axis. It's going to be your starting point. And in this case, we're just going to use the positive x-axis as our starting point. Again, just kind of a very typical, easy way to break it down and look at it. And then the angle from that is going to be our second coordinate. Okay, so that's polar coordinates, right? So instead of using instead of going this far in the x direction, this far in the y direction, my points are going to be represented by what angle am I up, how far of an angle I am from the axis, and how far I am from the center, right? This origin. Okay, which we can represent all the points in the Cartesian system just the same way in this polar coordinate system. And interestingly enough, we're going to have polar coordinate system actually is going to can repeat some depending on the angle and the radius we're at. So we're just going to go ahead and kind of hop into examples. I got a lot of examples to do today, so that's going to be the bulk of this lesson. As we kind of go through, we're going to be doing plotting the points, changing from Cartesian to polar. We're going to be kind of rewriting Cartesian equations in terms of polar coordinates or polar in terms of Cartesian. And then we're going to be just graphing some polar equations as they are, see how to plot them. And then at the very end, we'll do derivatives because derivatives are in the session. So we can kind of wrap all that up. So, okay, fantastic. Let's hop into it then. Okay, so we'll do here. So we're going to start with problem number 2 in the book, which says to plot the points whose polar coordinates are given. Okay, and we want to find, we're also going to add, in addition to this, to find two other pairs of polar coordinates of this point, of the same point. One with r is greater than 0 and r is less than 0. Okay, so I'm going to explain that second step in a bit, but first we're going to just take the point or points that we're given. We'll do a few here because it's got A, B, and C, and then we'll kind of talk about each of those. Okay, so we're going to start with A first. So A gives us the point 2 and 5 pi over 6. Okay, so again, let me reiterate. This is in polar coordinates, right? So I'm not plotting, this is not my x coordinate, this is not my y coordinate. What I have is a radius and I have an angle. Okay, so I have to plot it using the angle and then make sure to go out the distance of the radius, right? So whenever I'm plotting this point, so let me make a graph, right? My first step, generally, what I like to do is I like to take the angle and make sure, so this is going to be my polar axis in this case, right? Again, we're going to use our x-axis, positive x-axis as our basis. I'm going to go 5 pi over 6 from there, right? Now, where is 5 pi over 6? Which quadrant is that going to be in? Is that going to be in 1, 2, 3, or 4? It's going to be in 2, right? Because, I mean, it's less than pi, so it's definitely not going to be over here, but it's bigger than pi over 2. It's going to be in this section, so it's going to be something like this. Right, so that's going to be 5 pi over 6. Again, you can also just check and say, okay, that's less than pi, how far? That's about pi over 6, right? You're using reference angles, so they all remember doing reference angles and trig. Again, if you don't remember your trig values, you're going to have a lot of problems here. But this is the angle, okay? But I still need to go a distance of 2 out, right? From the pole, right? Which again is going to be your origin in this case. So this doesn't have to be exact. Just try to, like, you know, make sure you're being consistent, right? So if this is about 1 in the x direction, then I want to make sure to go about 1, 2, right? And so that's going to put me right here. Maybe I'll use a different color real fast, just to illustrate what exactly our point is here. But that is the point 2 and 5 pi over 6, right? Now, in terms of Cartesian coordinates, that's going to have some negative x and some positive y, and we'll get to that. But for now, we're just learning how to plot these points. Okay? Does that make sense so far? That is how you plot it. You just go around whatever angle it gives you, and you go out whatever the distance it gives you. Cool. Okay. Now, once I have that, it says to find 2 other pairs of polar coordinates of this point. One with r is greater than 0, and one is r less than 0. Okay. In polar coordinates, I can represent one point multiple ways, right? Because if I take this angle, right, for example, and I add 2 pi to it, that's going to put me in the same spot, right? Going 1 whole 2 pi around puts me in the same area, right? So an easy part for this, where it says r is greater than 0, right? If I want to find a point that has the same, puts you in the same area, all I need to do for the r is greater than 0, maybe I'll put that green over here, is I'm just going to add 2 pi to 5 pi over 6, or you can subtract 2 pi, it doesn't matter. It's going to put it in the same area, right? But ultimately, I want my radius to still be positive, right? For now, right? So I just need to go around one time. It's going to keep me in the same spot. So what is 5? How do I add these two together? What do I need to do? Yeah. Good. So an equivalent point in polar coordinates is going to be 2 and 17 pi over 6. Okay, again, because 17 pi over 6 goes to the same exact spot that 5 pi over 6 does. But in that case, I'm just circling around once and then stopping here, right? But then I still go out and there. Okay, it's the same exact thing. Good. And also, if you wanted to, you could subtract 2 pi as well and give you a negative angle, right? You would just go, so you would go around this way, but it's still be the same. Okay, so either way is fine. Okay, now we also want to do a case when r is less than 0. When r is less than 0. Okay, so that means that I want my radius to be negative, right? Now, we're not used to maybe seeing a radius be negative. We're used to thinking about it being positive. But whenever we say a negative radius in this case, if I was given the point, and maybe I'll use another color just to show this real fast. If I had the point -1 and pi/4, for example, right? And I was to plot this point, right? I would do my angle first again. So I would come up pi/4, which would put me, what is pi/4 in degrees? 45. So just kind of like halfway. So that's my angle, right? That's my theta in that case. However, since it's -1, what that means is that I don't go up 1. It means I need to make sure this line kind of cuts all the way through. And I'm going to go down 1 in this case. So that'll put me down here, right? So when I do -1 pi/4, I go to pi/4, but instead of going up, I go backwards. Okay, so that's what it means to have a negative radius. Okay, I just go backwards of what I expect to. Okay, does that make sense? Okay, so if I want to do r is less than 0, not for -1 pi/4, because that's already done, right? But for 2, 5 pi/6, right? I still want to end up in the same spot, right? So I want to end up here, right? And this, we'll use the blue. I want to end up here still. But in order to end up there, right, I have to go backwards, right, through the pole, just like I did here. So what I'm going to do is I'm going to take my line and kind of extend it, right? And so I want to figure out what, maybe I'll draw this one big so we can see it. I need to figure out what this angle is, right? What this angle is going to be, so that when I do -2, it'll put me back over here, right? And of course, you could go negative as well, but we'll just keep it simple and just keep it in the positive direction since it doesn't specify a negative angle. So this is 5 pi/6, this distance is, right? Here. How far do you think this distance is from here to here? How do you know that? That's correct. But how did you, I wasn't asking about the whole distance, I'm asking just this piece. Yeah, from here to here. How much is that? It's pi. Good, because it's a straight line, right? This is even from geometry, right? If I go from, if I have take my angle and I flatten it out perfectly, that's at 180 degrees, right? Or we're going to use pi radians in that case. So if I want to get the angle that's going to match with this r is less than 0 point, I'm going to take my angle that I'm given and add pi to it. Or again, you could subtract pi, it'll put you in the same spot. Regardless, either is fine, right? There's multiple examples you can use here. I just like to keep consistent and be like, oh, just add each time, and that's okay. So, like was already said, we're going to get, this is going to be 6 pi/6, 5 + 6 is 11. So we get 11 pi/6. So our point is going to be -2, 11 pi/6. Okay, awesome. Does that make sense to everybody there? Okay. Do you want me to do another example of this, of plotting one, or are you comfortable with this one? Can I move forward? Because there's a B and C as well I could do if you want me to, but if you're comfortable with this, then they're going to follow the same methodology. Okay, we'll call that good then. Let's go ahead and move on to the next section, which is going to be, let's see, I'll leave my definition. So this is going to be number 4. Number 1. So this says plot the point. Actually, I should have left. That's plot the point and then it's going to be in polar coordinates. So we're going to plot the point in polar coordinates. So that's going to be the first part. Okay. Then find the corresponding Cartesian coordinates. Okay, cool. So the example in this case we're going to be given, and I'll just do A for now, but if you want me to do another one, we can. We're going to have A, which is going to be 4 pi. Okay, so I want to plot this point in polar coordinates first, and then I want to find the corresponding Cartesian coordinates, right? Which I'm going to I'll demonstrate how to do that. But first, let's start off with just plotting this point, right? So, what quadrant are we going to be in on this graph? Third quadrant. Yep, 4 pi over 3 is going to take me all the way to the third quadrant, right? Here's 1 pi over 3, here's 2 pi over 3, here's 3 pi over 3. Okay, so that's going to give us that. Okay, and we go out a distance of what? 4. So again, you might just want to make sure you're consistent. We'll call that 1, 2, 3, 4. That's going to be my point. Again, maybe I'll use another color on that real fast just to separate it from the rest. So let's know that that's my point. That is 4 pi over 3. Okay. So now the question becomes, how do I find this in terms of Cartesian coordinates? Okay. Well, let's think about this. Right. If I were to take this picture, right? Notice we have this kind of ray that's going to come down that point, right? What if I take from that, I'm going to draw a straight line upwards to my graph, and I'm going to connect these two lines together, right? What's that shape I have there? Right triangle. Yeah, it's a right triangle, right? Triangle in specific, a right triangle, right? Now, if we look at this right triangle that I have, right, this distance is going to be the x coordinate, right? Because if I go that far left and right, that's my x coordinate, right? And this distance right here is going to be my y coordinate, right? So in order to figure out what x and y are in terms of this r and this theta, right, I'm going to use this triangle to help me out, right? Now, let's assume for the moment, right, that I don't know exactly what the r and theta are. Let's just do them in general. Okay, so this distance right here, this is going to be r, and then this angle here, we'll call is going to be my theta, but we can really just kind of represent it in here for now, because it'll give us the same value regardless. So let's first try to figure out the y, so we'll do the y first. Why not? Okay. On this triangle, right, if my angle is here, y is what side of the triangle compared to that angle? It's the opposite side, right? Okay. We should be given the hypotenuse, which is r, right? So what trig function relates the opposite side to the hypotenuse? Sine does, right? So sine of the angle of this triangle, sine of theta, should be the opposite side, which is y, over the hypotenuse, which is r. Okay. What about x now? X is what side of the triangle? The adjacent side. So if I know the adjacent side and the hypotenuse, what trig function relates those? Cosine. So we get cosine theta is x over r. Okay. If I know theta and I know r, right, can I use these equations to solve for x and y? Yeah, we're going to multiply this one by r, we're going to multiply this one by r. Okay, which in the end is going to give us, maybe I'll use orange just to really bring this out to us, x, y. The coordinates in terms of x and y is going to be equal to r times cosine theta for x, and r times sine theta for y. Okay, so if I want to get x and y, I just take the cosine of the angle multiplied by r to get x, and I take the sine of the angle times r to get y. Okay, so let's apply that here in our example. Okay, what is, right, so what's my radius in this case? 4. And what's my angle? Well, yeah, we still want to use 4 pi over 3, right? Even though we're kind of using a reference angle idea here for that, it still holds true even for the bigger angle. Okay, so we get 4 cosine of 4 pi over 3. Okay, let's work through this real fast. So we have cosine of 4 pi over 3. Okay, so what's the reference angle we're going to use for this? For 4 pi over 3? What is it? Right? Just take out the 4. It's pi over 3, right? Okay. What's the cosine of pi over 3? Not root 3 over 2. What's the other one? 1/2. Okay. So it's 1/2. And then what quadrant are we in? We're in the third quadrant. Is cosine positive or negative in the third quadrant? It's negative. So we're going to have 4 times negative 1/2, which is what? What is it? Well, it's 4. It's just 4 times negative 1/2, right? So it's just 4 divided by 2. Yeah, it's times minus 1/2, right? Because it's 4 times cosine of 4 pi over 3. So we just get negative 2. Okay, so I'll write it back. Negative 2. Okay, so we really don't have time to review over reference angles and stuff. So try to make sure you just kind of think about it yourself. But you just find it, just as a quick sort of reminder, you're going to use whatever the angle is from the x-axis, right, as the reference for that guy, and you should have those values memorized, and then you just use the quadrant to determine the sign. Okay, good. So we get negative 2 here, and y is going to be for sine of pi over 3. Okay, so we use the same reference angle. What's sine of pi over 3? Sine of pi over 3. Root 3 over 2, and we're in the third quadrant still, so is sine positive or negative? Negative. Good. And you should also be able to tell just from where your point is, right? They should both have negative values on it. So I'm going to get 4 times negative root 3 over 2, which can't work out as nicely, but that's okay. We can still do 4 divided by 2, so we're going to get negative 2, 3. So in the end, this point in Cartesian coordinates is going to be negative 2 and negative 2. Okay? Good. So I use these equations to calculate what my point is going to be in Cartesian coordinates. Okay? And we're also going to end up using this relationship to be able to convert back. But I want to ask first, does this make sense to everybody? Do I need to do another example, or can I move forward? Yes.
Could you use sine squared?
Well, you would have to include the r somehow, right? Because y is r sine theta, not just sine theta.
So if 1 was 4.
What is it?
So if 1 was 4.
If 1 was 1 was I guess I'm not exactly sure. I mean, because it's 4 here, you're saying if this is 1,
Yeah.
or I mean, if it was 1, maybe.
Radius was 4.
Yeah, so you would, okay, yeah, it's gonna end up being 4 squared. I think there's probably easier ways to do it. These are just a lot easier to use. I would just use these ones, right? Because you're going to be given the radius and the angle, right? So you just plug them in. You don't even have to solve anything. You just kind of plug them through those equations. You got it. Okay, so I would recommend that. Okay, so everyone's good on this? I want to move forward to the next one. Okay, great. So the next part, number 6 here, we're gonna be given the Cartesian coordinates of a point. My coordinate over here. So if you want to like move in, right, so you can. Okay, that'd be great. we're going to be given the Cartesian coordinates of the point in this case, and we're going to find the polar coordinates now from that Cartesian point. Okay. Good. So, and we don't have to graph it this time if we don't want to, but maybe it might help in some cases. So let's do. I did that one in green. We can do. A Cartesian point given, find polar coordinate where theta is in between 0 and 2 pi, where r is greater than 0, and we also want to find polar coordinate where, again, we want 0 to be less than theta, which is less than 2 pi. I say less than 2 pi because 0 and 2 pi give you the same angle, right? So we don't need to include both of them. Where r is less than 0. Okay, so I want to take that point and I want to represent it in both ways. Okay, I'm going to do one where r is greater than 0, one where r is less than 0. Okay, so the point we're going to be given here is the point square root of 3 negative. Okay, so so maybe I'll draw a picture real fast because again we want to kind of get our equations here. So I'll do it. Right, so here's our, we want to go to root 3, 1, 2, so it's going to be about here, and we're going to go down -1, put us here, right? So I'm just graphing that in terms of Cartesian points because that's Cartesian. So we go out root 3 and down -1 or down 1. I guess in that case, not down -1, we'll go the opposite way of 1. Okay, so again, from here we can create, sort of a triangle shape to help us do this, right? Now, if I want to figure out what the radius is and what the angle is, right, for my point, right, we still have a certain x piece of it, we still have a certain y piece of it, right? Now, the hypotenuse of that triangle is supposed to be r, right? And again, this is a right triangle. So if I know x and I know y, is there a way I can find what r is supposed to be? By the Pythagorean theorem. So, and normally, well, you might see it like this. Am I right? Well, I'm going to write it as r. So we do r squared equals x squared plus y squared, right? X squared plus y squared is r squared. Where we're going to, or you can write this as r is plus or minus x squared plus y squared, right? Now, if they don't give otherwise, you can just assume it's a positive one. But we see in this example, we want positive and negative, so it can go other way, okay? But I just take x squared plus y squared and then take the square root of it. And that's going to be my radius value, okay? Sign, depending, generally positive, but we just want to follow the directions, okay? Now for the angle, right? So again, you could think, oh, maybe the angle's here, or you could really think about kind of the bigger one. It doesn't matter, whatever way you represent it, they're in the same spot, okay? I don't know r again. We're going to assume I don't know r. If you do know r, you might just be able to use one of those equations to solve for it. But let's just go without that because there's an easier way. I think we can determine the angle directly. Okay. So if I just want to relate x and y together on a triangle, right? Y is the opposite side and x is the adjacent side, right? Just like they were over there, right? What trig function relates opposite and adjacent together? Tangent does, right? So the tangent of my angle, of whatever the angle is, no matter if you use the bigger one or the smaller piece, right, is going to be the opposite side, which is y, over the adjacent side, which is x. Okay. Now, again, like I said, you find r and then solve using, like, if you know x and r, you can solve for cosine theta. But I think this is going to be your best method. And the reason why I say this is because y in this case sort of represents, right, it's the opposite side of your triangle, right? So in a sense, y is representing the the sine of my triangle, okay? X is the adjacent side, right? So in a sense, X is representing the cosine of my triangle, okay? So let me give you a few scenarios, right? To help us understand why setting it up in this way might be the most helpful to us, right? So in our case, right, we have positive X and we have negative Y, right? So that means, so I have negative positive, so that means my sine is negative and my cosine is positive. If my sine is negative and my cosine is positive, what quadrant am I in on the triangle? Right? Am I in this quadrant? Yeah, we have to be in the fourth quadrant, right? Because cosine is positive here, but sine is negative, right? So that immediately tells you the theta has to be in the fourth quadrant, right? Now, the reason why we want to specify that distinction before, like really dividing the numbers, right, is because if I just did, -1 over √3, I might just bring that negative out in front and say, oh, well, it's negative. Well, tangent could be negative here or here. But doing it before you do the division helps you to point directly to where it's supposed to be at, if that kind of makes sense, right? So I would recommend you use tangent and then kind of think about the signs, right? And we'll do the example here again just to demonstrate that. But these are my equations here. So we have R is square root of x squared plus y squared. Again, assume positive until otherwise, and then tangent theta is going to be y over x. Okay, and then we can solve the theta. Okay, so R is going to be the square root of x squared plus y squared. So we're going to take square root of 3 squared plus -1 squared. What's the square root of 3 squared? 3. What's -1 squared? We get square root of 3 plus 1, which is what? 2. Good. So my radius in this case needs to be 2. Good. Okay. Now, so we'll just use the positive one for right now. We'll start with this first point here. Okay. That would be nice and easy. Okay. Tangent of my angle, right, is supposed to be -1 over √3, right? Which we said, okay, since it's negative on the top, that's sine. Since it's positive on the bottom, that's cosine. I'm in the fourth quadrant. Okay. So first of all, ignoring the negative sign, what angle gives me 1 over √3 for tangent? Anybody remember what that one's going to be? Good. Pi over 6. So that's my reference angle. So maybe I'll write like theta ref is going to be pi over 6. Okay. But I need to find what the equivalent angle is in the fourth quadrant that's in between 0 and 2 pi. Okay. So how do I find that angle? All right, what do I do? All right, we're saying the reference angle, so maybe I'll use a different color again. Our reference angle is pi over 6. Good. Yeah, so we're going to get 11 pi over 6, right? Because we're going to take the whole 2 pi all the way around, and then we're going to take off that pi over 6 from it. So we take 2 pi minus 11 pi over 6, or sorry, 2 pi minus pi over 6. So then we get that theta equals 11. Good. So in this case, so to find the polar coordinate, 0 is less than or equal to theta is less than 2 pi, where r is greater than 0, we're going to get the point 2, 11 pi over 6. Okay. Is everyone following that? Okay. Again, to get your radius and your theta, just use the 2 equations, right? And use the tangent one very carefully, right? Because if I know the distinction between the top and the bottom, right, I can see what's positive, what's negative, and it gives me the quadrant. Okay, good. Now I want to get the polar coordinate where r is less than 0, right? So we already know we want -2 instead. Okay. So let's see if I want to. So on the first problem, right? we just said to add pi to the angle, and that's gonna give us the one, what we want, right? However, what's gonna happen if I add pi to this angle? It's bigger than 2 pi, so I can't have that. So we're going to subtract pi instead. It's still gonna give us the same effect, right? But we're gonna be still inside the range I want, okay? So we want to do, so we're gonna take 11 pi over 6 minus pi, okay? Which is gonna be 11 pi over 6 minus 6 pi over 6. Let's leave this 1. 5 pi over 6. So we get -2, 5 pi over 6. Okay, good. So this and this both represent the point √3, -1 in polar coordinates. One does it with a positive radius, one does it with a negative radius, right? Within 0 to 2 pi at least. Obviously, there's more examples than that, but within 0 to 2 pi, these are only 2 options. Okay, questions here? Comments, concerns? Nope. Yes. Yeah, absolutely. So we were given -1 over √3, right, for our tangent, right? And we said, let's ignore the negative sign for now, because the sign part will come in later. We want to remember what angle, right, in our 0 to 90 range, or 0 to pi over 2 range, are we going to get 1 over √3, or √3 over 3, which you should hopefully remember is going to be pi over 6. So now I take that pi over 6, and I'm going to come down from the x-axis into the 4th quadrant, right? Because we also established that since we have -1 and √3, we're down here in the 4th quadrant. So I need the angle in the 4th quadrant. So I came down pi over 6 into the 4th quadrant, and then in order to get what the actual angle was, I just took pi over 6 and subtracted it from 2 pi, right? Because if the whole angle is 2 pi, and I just take off the little pi over 6 piece, I get 11 pi over 6. Okay, does that make sense?
Be able to just like, because did you know the 3 points, like the 3 points that are in each point?
Mhm.
You know, it wouldn't be like wouldn't be the middle one. You know what I mean? It would have to be the top one because the x and the y values are not the same. So you would have to be 11 over 6. Because that's how I did it in my head.
I mean, there might be other ways to think about it, which is completely fine. This is how it's generally taught, but if you're, the only thing to really be careful of, like whatever way you do it is okay. Just the only thing to be careful of is just to recognize the sign distinction, right? If the numerator has a sign versus if the denominator does, or maybe they both might have one, depending like if I have -1, -1, right? Because that's gonna change where we get put at. Right, because if I just took this negative and just threw it out in front, it's a bit kind of ambiguous as to which quadrant it's in. Maybe, I mean, you could see it, obviously, if you plotted the point, but if you didn't, maybe you wouldn't think about that at first. So, whatever way you think about it, it's fine. Just as long as it makes sense. I won't. Any other questions? Okay. Good. So, that's plotting the points in general, right? Just taking my different coordinates, plugging them in. So the big equations to remember here are r cosine theta, r sine theta for x and y, and r is the square root of x squared plus y squared, and tangent theta is y for x. Okay? If you remember those, you should be able to convert easily between the two of them, like, as agreed. Okay? And there shouldn't be any issue. Great. Now let's move on to some of the more fun parts here. Okay. So now we're going to do problem number 8. Problem number 8 says to sketch the region of the plane region of the plane consisting of points whose polar coordinates satisfy following condition. So in this case, I'm going to be given a set of like radius or angle potentially, and I want to sketch the region that's going to satisfy what I'm given, right? So I'm given 0 is less than or equal to a radius is less than 2, and pi is less than or equal to theta, which is less than 3 pi over 2. Let me make sure is that equal. It's equal to less than or equal to 3 pi over 2. So this is the region I want to sketch. Okay. So I need, so whatever, all the points that I'm going to consider need to be between radius 0 and 2 and between pi and 3 pi over 2. Right? So let's take the graph. Right? So let's say here's 1, 2, 1, 2, 2. Okay. So on this picture, right? Again, if we assume our polar axis is the positive x-axis, where is my angle pi going to be? Right, where's this angle? Yeah, it's just the left side, right? Doesn't need nothing too complicated. I don't need you to give me a perfect explanation. I just want to know that you know the general direction, right? So it's going to be, so pi is right here. Okay, I might not use all of that, but I recognize that at least I include the angle pi. Okay. I also include the angle 3 pi over 2, which is where? Up, down, left, right. Straight down. Okay. And everything in between here, right? Every angle in between, I can include that. Right? Now, I might not include everything, right? Because we still have to worry about the radius. But at least for now, my angle includes all of this. Nothing else is included here. Okay. Now my radius only goes from 0 until 2, right? From 0 until 2. So can my radius be 2? No, it cannot, right? So, right, if I was on pi, right, I couldn't have a radius of 2 here. I'm going to make that a dotted line. And I couldn't have a radius of 2 here. Again, dotted, right? And everything as I circle around, I cannot include that radius of 2, right? Do we see that? The radius, right, is the distance from the origin, right? So it needs to circle around. I can't just make like a block, right? Because that wouldn't make sense. I need to circle my radius around like this, right? Now I can include 0, which would be this point, and I can include everything in between. So my final answer, right, is to see where all that crosses over. Again, I can't get anything out here. So it's going to be all of this space. Side, again, making a distinction that okay, so that is the region that matches to those inequalities, those ranges. Okay, do we see that picture? Does that make sense? Okay, good. So that's all it is. If they give you points like that, you just need to make sure your region kind of corresponds to that. Okay, good. Let's see. So I have, okay, next one, right, is we're not just going to take points and we're not just going to take random regions, but I'm going to take equations. And at least for our class time now, we're going to be taking equations that are in terms of polar coordinates, right? Because polar equations might be a little bit harder for us to graph in general. And we're going to take those equations and we're going to convert them into Cartesian equations, right? Because those are the ones to work with. So, so we're going to see, and this will be 16 and 20. identify the curve by finding a Artesian equation. So I did two because I figured, it might be good to kind of see it. And I got the first one's just like a real silly example. The first one, 16, is going to be R equals 4 secant theta. Okay, so I'm given this equation in polar coordinates, right? So if I have an equation in polar coordinates, right, it should just be R theta in some way. And so I want to take this and identify what the curve is by getting a Cartesian equation for it. Okay. So it doesn't look like I can do anything at first. I mean, I know for sure how to convert R in terms of X and Y, right? Maybe I'll write on the side for us. All right, we know R is the square root of X squared plus Y squared, but we don't really know much about secant. Okay, so maybe instead of secant, right, we do use cosine a lot. So maybe what should I do to the secant? What is it? Okay, yeah, that sounds good. So I'm gonna rewrite this as R equals 4 over cosine, and maybe we'll even take it one step further. Instead of leaving that cosine in the denominator, I'll multiply it up. So I'm gonna get R cosine theta equals 4. Okay, what do I know about R cosine theta? Do I know that's equal to something? It's X. So if that's equal to X, I just replace it with X. So I get X. So what is that? What is X equals 4? It's a line. What sort of line? It's a vertical line. It's a vertical line through X through the number 4. So that's it. You're done. Okay, does that make sense? Good there? Okay, so I was just trying to mess around with my equation a little bit to see if I could get anything from it, right? So there's that. Yes.
Why is R cosine theta?
So that is because on example 4, I'm not sure if you made it before we finish that one. But we learned that using a triangle, right? We found that X is equal to R cosine theta and Y equals R sine theta. And that's because if I take a triangle, right, that I know a theta and I know an R to it, this is X and this is Y. So if I take the sine of this triangle, it's Y over R. So Y is going to be R times sine theta. And if I take the cosine, I get cosine is X over R. So X is R. Okay, so that's how we get these relationships. Okay, let's do another one. I'll do this one in orange real fast. We're going to do 20 R squared sine 2 theta equals 1. Okay. So I want to figure out what this equation is, right? So any ideas? What might be a good idea for this one? All right. Maybe I don't like sine 2 theta. Is there some way I can rewrite that? Good. So this is my double angle, right? And we have our double angle identities, right? Which again might be something you want to remember. Because sine of 2 theta is the same thing as 2 sine theta cosine theta. Now, what I'm going to do is I notice that I have sine and I have cosine, right? And I have 2 R's. So I'm going to take 1 R and I'm going to give it to each trig function. So I'm going to give 1 R, and I'll leave the 2 outside. I'm going to give 1 R to sine, and I'm going to give 1 R cosine. Equal to 1. Okay. Right. So X is our cosine theta and Y is our sine theta. So we get 2 times Y times X equals 1, or I can write this simply as, yeah, so we get 2xy, 2yx. If I do choose to solve this for Y, I get Y equals 1 over 2x. Okay, so this is a rational function, right? It's a, you know, we're used to this sort of curve. It's, let's see, the technical name is it's a kind of a rotated hyperbola if you look at it, but you can call it whatever you want, just a rational function where we have a number over x. Okay, does that make sense? Is that good? Okay, that's the process. Okay, now you're going to, you know, you might have cases, and maybe I can't remember if I assigned this one to you. Right, you really just need to be inventive here when you're doing these sorts of problems, right? Again, I can't remember if I assigned this one for sure. I probably did, but there's one in the book that looks like this. Okay. So I would encourage you to test this one out on your own and try to figure it out, because it will be a little different than these. But I have this cosine and I have r. If there's an r on this cosine, I could change it in terms of x. And if this was r squared, then I could just easily, you know, pretty easy to write that down the square root. So I would take both sides of this and multiply it by an r. Okay, and then from there it should be something you're familiar with. Okay, so I'll leave it at that just so I don't mind, because I ran a little on time, but I wanted to do the 2 even examples. Okay, anything else? Any questions for me on this? Okay. Hopefully, mostly straightforward. Just you have this equation, this equation, this equation. And maybe tangent, I doubt you'll use that one as much, just for what most of the problems are, but just try to rewrite them in a way that you can use those in some way, right? R is the square root of x squared plus y squared, or even r squared. Doesn't matter. Okay, good. So now let's get to kind of the hardest part of this section. There's a section right after this one in the book, which I assign some problems to, where you convert a Cartesian equation to a polar equation, but that one's like a lot easier. You just have to plug in these, right? And then you're kind of set. If you have x squared plus y squared, you could use r squared, but you would get the same thing out of this. So don't stress about that. The harder part is doing these ones, so I wanted to cover that. Okay, for these. For this last section, we're going to okay. So the reading of the instructions for the book on this say simply sketch the curve with the given polar equation by first sketching the graph of r as a function of theta and Cartesian coordinates. So I'm going to be doing that, but what I want to say is, even if it didn't say that by first sketching the graph of r in terms of, you know, theta and Cartesian coordinates, I would recommend you do that every time, just because it makes graphing the polar equations a lot easier. Okay. Essentially, here's what I mean. So we're going to do number 30, which is r equals 1 minus cosine theta. Okay. So there's going to be a big gap, right, for us to somehow just go from this to immediately trying to graph it in terms of the polar coordinates, because we're not used to doing that, right, in terms of how the movement goes, what it looks like. However, if I treated this like a Cartesian equation, so I had like y equals 1 minus cosine x, we also know how to graph that, correct? We all know how to graph trig functions, hopefully. So we're going to start with that. So I'm going to make a graph, and I'm going to let, make sure there's plenty of room going in this direction. We're going to let my x-axis, in this case, be my theta axis, and we're going to let my y-axis, in this case, be the r-axis. Okay, and I'm going to graph this as I would graph cosine. Okay, now, so let's kind of get our major points here on this graph. So feel free if you need to, you can kind of pull up, you can do the whole table, right? Theta and R, what theta is this, what's R gonna be? You know, it should be pretty quick. So, but let's just plot our points, right? So, well, actually, let's just instead of doing that, this is a pretty simple equation. So let's break it down into its pieces, right? First, cosine theta. If I'm graphing cosine theta, do I start at 0 or do I start at 1? 1. So we're going to start here, right? And then it goes down, right? And hits 0 at what angle? Pi over 2. Good. And then it's going to come down here to -1 at what angle? Pi. And then it comes up 3 pi over 2, and then it's going to circle back up. And so this is one loop of cosine. Okay, we only need to do one loop, like one set of all the way to 2 pi in these problems, because that'll fill our whole polar graph if we do all the way to 2 pi. Okay, so this is good for now. So this is cosine x. But obviously I don't want cosine x, I'm going to end with 1 minus cosine x. Now, what's going to happen if I put that minus on it? All right, just if I do minus cosine x instead. What is it? Yeah, you flip it over the x-axis, right? This is or reflect it over the x-axis. So we're gonna get this. Okay. Finally, if I want to do 1 minus cosine x, what is that one gonna do? It's gonna shift it up 1 spot. So that means every value on here is gonna come up 1. So this is going to be my final graph. So it's going to look something like this. Okay. Now, again, if you want to track, you can find some exact points. So we can calculate it for sure. This is going to be, so it was 0 here. So if I add 1 to it, what's that going to be? 1. Okay. It was 1 here, so it's going to be 2 here, 1, and 0 again. And then this was at pi over 2. This is at pi. This is at 3 pi over 2. 2 pi. Okay, so I just did kind of my different pieces before I just put it all together, right? Again, you can always just do a table if you want to. And I might do that for the next one, so we have a bit of variety. But this is going to be that purple part, which I would especially highlight, is the graph that I'm focusing on, okay? Because now what I'm going to do is I'm going to take that graph, and now I'm going to put it on the regular axis. So we're going to have x here and y here. Okay? So let's just follow this around. Here, right? My theta is what here? 0. What's my radius here? Okay. So we're going to start. I'm going to start at 0, 0. Okay. Next, whenever I'm at pi over 2, I'm going to be at 1. Right? So whenever I'm at pi over 2, right? So that's my angle. Right? Here's my 90-degree angle, pi over 2. I need to be up at 1. Okay. In the meantime, are my numbers getting more positive or more negative? They're getting more positive, right? So as I swing around, right, to that point, my values, my radius should continue to increase. So I should be seeing something like this. Okay. Right? They shouldn't bend backwards or something, right? Your angle's here, right? And so you want your radius to come out towards the positive direction of the angle. And that's going to give us part of the shape for now. Okay, so that's to here. Next, at pi, I'm going to be at 2, right? So 1, 2, we have this point, and this one's even a little easier to see, right? I just need to connect this point to that point. So it's going to go to here. Okay, pi over 2, we're at 1 again. So there, again, it's always positive, so that this isn't too hard to draw. We're going to end up here. And then finally, we're going to circle back to 0, right? So when we get to that 2 pi spot, my values are still positive, so I should still be rounding out this way, but I'm going to go back to that center. So I'm going to go back. And then the graph is going to start itself again and again and again, right? But this, maybe I'll erase a bit of the ink there. This is going to be my polar graph, right? Which I may not have drawn this perfectly in terms of where the curve goes, but the idea is just to sketch it, right? So it looks kind of like a heart, right? Cool. So this is my polar graph. Okay, how's that? We're gonna do 2 examples, so don't worry, we'll do another one. But that's the idea, right? I draw the normal trig graph like I'd expected, and then I use the details, use what I know, right, to plot it here. The blue and the white don't contribute to this. That was just me plotting the purple curve, but okay. Any questions on that one? Okay, nope, sounds good. So let's now move on to the second example, which has the same directions. We're going to do number 36 this time. And make sure I don't erase this one because I need to leave this up to 10.4. Let's see. So I'll use, well, maybe use blue. So I'll use that one. 36. Our function in this case is going to be r equals negative sine phi theta. Okay. Negative sine phi theta. So again, we first want to start out and we want to graph the function as if it was a Cartesian graph. So I'm going to have theta on the x-axis, r on the y-axis. Okay. So again, maybe in this case we'll just do like some plotting some points sort of thing. But before we get to that, right? We remember how to talk about like amplitude and like period and the sort of thing on this graph, because that's going to help us a lot when we're plotting this. We need to remember these points, right? So what is the amplitude of this sine graph going to be? It's going to be 20, right? Now, what is the period of this graph going to be? Who remembers how to find that? Right? What's the normal period of a sine and cosine graph? If there's no number multiplying inside, what is the period of sine and cosine? Right. Well, it's just 2 pi, right? Just like we go from 0 to 2 pi. That's like the distance we travel, but the period itself is the distance. 2 pi over 5. Okay. The reason I wanted to do that is because that's going to be important, right? Again, as I mentioned already, I want to go all the way to 2 pi, right? Because I want to cover all of my distance around. This one was fine because the period was 2 pi already, so that one was easy. But this one's 2 pi over 5, so I need to go, and maybe I'll make this bigger. I need to go 1, 2, 3, 4, 5. We're going to have 2 pi over 5, 4 pi over 5, 6 pi over 5, 8 pi over 5, and eventually the rest. Okay? I want to get to 2 pi, so I'm going to need to take 5 periods of this graph. Excuse me. Okay. Now, in between there, right, in between each of these sections, we just have like a normal sine graph, right? So our sine would go up and then down, and up and then down, and up and then, well, I guess if it was positive sine, how does negative sine go? Right? Normal sine looks like this typically, right? So what is my negative sine going to do? It's going to go the other way. So we're going to go up, up, up. right? So, and I would recommend if you can, you don't have to get all the, exactly what some of these points are. You can if you want to break it down more. These middle points where we hit 0 are going to be pretty easy to find, right? Because it's just halfway between each of the periods. So we're going to have 0 plus 2 pi over 5 divided by 2, which just gives us pi over 5, 3 pi over 5, 5 pi over 5, which is pi. We're going to have 7 pi over 5, and 9 pi over 5. And if you want to get points in between, you can. I'm going to try to do this without having to repeat those exact values, but we have kind of the big points in between that are easy to calculate. Okay, so let's go ahead and try to start plotting our graph now at this point, which we're going to have. Let's see. I'll put this still. Switch. I'll just do the curve in white so we can see it. Okay, now I'm going to figure out where each of these kind of significant points are. So I'm gonna try to plot them on my graph. So we have 2 pi, of course, is you define. So when it comes to 2 pi over 5, 4 pi over 5, 6 pi, 8 pi, we're just going to be taking this picture and just trying to split it up in something like this, right? Kind of split it into fifths, right? I want to go, this is 2 pi over 5, this is 4 pi over 5, et cetera, right? I want to plot these major angles for myself so I can have them as I'm working through and getting to each point, right? And I'll also add in the pi over 5, 3 pi over 5, blah, 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 whatever, the other points in the middle, right? So we have, so these are, maybe I'll do these ones as bigger dashed lines and I'll mark them. Two pi over 5, 4 pi over 5, 6 pi over 5, 8 pi over 5. This is 0 or 2 pi. And then we're going to have middle, pi over 5. Okay, in the middle here, somewhere approximately, we're going to have 3 pi over 5. And in the middle of these two, which is just pi. In the middle of these two, we're going to have 7 pi over 5. So these two are going to have, okay, and that's going to help us to have all this, like all the points that we need. Okay, so let's just go through this very slowly. Okay, as we're working through. Okay, from 0 to pi over 5. Right, from 0 to pi over 5. Is my graph in the negative range or positive range? It's in the negative range, right? So what's going to happen from 0 to pi over 5 is I need to, I'm kind of going through this angle, right? From 0 to pi over 5, I need to go circle down a little bit, and I'll call this 1 for now. And I need to circle up. Right, because it goes negative, so it needs to go in the opposite direction, but then it comes back up. So we have kind of a leaf there in a way. See it like a little leaf. Okay. Next, we're going to go from pi over 5 to 2 pi over 5. So, but in that case, am I positive or negative? Positive. So this one's a little bit easier. I just kind of need to stay in between that section I've drawn. Okay. Usually, if you like kind of put all these different lines on here, these little, the little leaves you're drawing, the little stems should be within the different angles. Okay, from here, from 2 pi over 5 to 3 pi over 5, I'm in the negative range again, right? So normally I'd be here, but now I want to be across the way, so I'm going to be down, let's see, looks like that would be there. I want to be down in this section. Yep, we'll do something like that. And maybe a bit big. Let me shorten that. Okay, 3 pi to 4 pi. So here to here, I am in the positive again, so I get another nice stem that just comes straight out. And then 4 pi to 5 pi, I'm in the negative range, so that's going to put me down here, because normally I'd be going from here to here, but instead I go in between the angles across, like the angle across from it. From here, we're basically done, because if you notice, pi to 6 pi or 5 is in the positive, but we've already done that one. That's this guy. 6 pi to 7 pi goes in the negative, but that would be this guy. 7 pi to 8 pi would be here, typically, if that's in the positive. We already did that one. 8 to 9 would be in the negative, but that's here. And then 9 pi to 2 pi would be positive, but it's already there. Okay, so putting all of our information together, this is going to be my graph. Okay, I understand this is difficult. Whenever I took this class, I had struggled to understand it first, or at least when I took 171, I guess, because by the time I got through not too, they're a little difficult. You just need to take your time, right? Give yourself as many points as you want. Like seriously, if you want to just make a huge table that lists like so many different points, and you want to plug them in, right? If I take pi over 5 and put it in there, I just get started 5 over 0, right? I can just take these different points in, right? I just knew the graph looked like, so I used that for my shape, so I can save a bit of time. But you could just plot it, right? It's the same thing as you're just graphing a normal equation. I can plot points to get the graph, or I can kind of use a general basis. Okay, so again, I understand it's difficult. I'll if I give you one on a test, I promise it will probably be more something like this, so it's not too hard. But you do need to grasp that, at least a little bit. Okay, it's okay if it takes some time. You at least understand what's going on behind it, what the idea is. Okay, if you want to, kind of practice more with it, you can talk to me. I'd be happy to do more examples with you and do the book it gives as well. Okay, yes.
If I were to like just make a table, so the graph, so that how would I know that there's
How would you know that there's nothing
like nothing on that line? How would I know it's ignoring?
nor what?
I would like to see how the.
Oh, how to know there's nothing here?
Yeah, would it just-
Well, that's why I'm saying you can do points. I would recommend drawing a graph too, though, because that will really show it. And there's just technically something on Pyro too. It's just because that's going to be probably somewhere. Let's see. That it's a little hard to see. I mean, there's still a point at Pyro too. It just looks like it might be in the negative range a bit, so it's going to be in an odd spot, right? So I wouldn't like in this case. Pyro 2 is not the best example to do, just because I mean you could actually find Pyro 2 pretty. That would just be. Anyway, I would draw the graph. If you did the table, that's fine, but it's good to have the graph as well. Okay. Good. Again, I'm happy to do more like that, but that is that's kind of an easy one, harder one. Take for what you will, do what you will, make a table. That's fine. Okay. So to wrap up real fast. And again, if you don't sketch it perfectly, that's fine. Maybe if you just know, have a general idea what it will look like, just try to fit it in. It's gonna need to be. Okay, real quick, and then we'll take a break. But this section is longer than all the other sections, so I will take a little bit. We're going to talk about derivatives real fast, okay? But it's just a pretty straightforward equation. So whenever I'm taking a derivative, right? Again, we're not just gonna do derivatives like, oh, dr over d theta, like just the derivative of that thing. But I want to understand the rate in terms of the x-axis and the y-axis, kind of my dy over dx. Okay, so I want to find dy over dx. Okay. Now, whenever I'm finding this rate, right, the y and the x that I'm using here are the same y and x that we talked about earlier, where we're going to have y equals r sine theta, and x equals r cosine theta, right? But given a specific graph, r, right, might be something like negative sine of 5 theta, right? So it might be some function of theta. So y equals r sine theta, or maybe I'll think about that as f of theta sine theta. So it's a function of theta. X is r cosec theta, or f of theta cosine theta. So all that to say, y is in terms of theta and x is in terms of theta, right? And so it's a little bit reminiscent of our parametric equations, right? So I'm going to start that off similarly, okay? Where I'm going to have dy over d theta over dx over theta. However, I may not want to worry about going through the trouble of like, oh, let me write out y and x first and then try to differentiate it. I just want to write it in general so I can just plug my r and my radius in directly and get my answer, okay? So what we're going to do, right, again, y is the same thing as r times sine theta, or where r is a function of theta, right? So I have one function of theta times another function of theta. How do I take the derivative of that? We have to use product rule, right? So take the derivative of y with respect to theta. What is that derivative going to be? So we're going to have, right, we're going to have f prime theta times sine theta. I want to write that as dr over d theta, right? Just the derivative of r with respect to theta times sine theta plus r, right? We leave r alone, times cosine theta. Right. We won't worry about writing that as x here, just again, so we can just plug directly in with the r and theta, but yes, you're right. And then x, it follows very similarly, so I'll just finish that one real fast for us. We're going to get dr over d theta cosine theta, but instead of plus r sine theta, what's the derivative of cosine? Negative sine, so we're going to get minus r sine theta. So the derivative, the dy over dx is equal to dy over theta over dx over d theta, which is dr over d theta sine theta plus r cosine theta, all divided by dr over d theta cosine theta minus r sine theta. So that is the expression for a derivative of these polar graphs. Okay, so I'm going to use that formula to find my derivative. So let's use that formula to find our derivative. I can't erase that. I can delete that. I'll go over here real fast. I think we know what polar graphs are by this point, hopefully. Okay. So we're going to do number 56. Number 56. Which is going to be, so we're just finding the derivative. So I'll just say find derivative. So we're going to have r equals 2 plus sine 3 theta, where theta equals pi over 4. Theta equals pi over 4. So I want to find it at a particular point. Okay. So if I want to find the derivative, I'm just going to plug it into the formula. So we're going to have dy over dx equals dr over d theta sine theta plus r cosine theta over dr over d theta cosine theta minus r sine theta. Okay. So what is dr over d theta going to be in this case? What is it? So a derivative of r respect to theta. What happens to those two? Disappears. All right. What's the derivative of sine? Cosine. So we get 3 cosine 3 theta. Okay, remember chain rule. I do the derivative of the outside, which in the outside in this case is sine. Derivative of sine is cosine. And then I multiply by the derivative of the inside, which is going to be 3. Okay. So I'm going to take that 3 cosine 3 theta along with my r, and I'm going to plug it in here. So we're going to get 3 cosine 3 theta times sine theta plus 2 plus sine 3 theta, right? Because that's r. Cosine theta over 3 cosine 3 theta times cosine theta minus 2 plus sine 3 theta times sine theta. Okay, and we want to do this of pi over 4, right? So let's get everything real fast, okay? So if I put pi over 4 into 3 theta, right? I'm going to get 3 pi over 4. What is the cosine of 3? What's the cosine of pi over 4? 1 over square root of 2, or I'll write it as square root of 2 over 2. And then it's 3 pi over 4, so is that going to be in, what quadrant is that going to be in? First, second, third, fourth? Second, good. So is that positive or negative? For cosine, right? Let me negative. So we're here, a cosine is negative in that quadrant. So we're going to get negative 3 times the square root of 2 over 2. Sine of pi over 4? Square root of 2 over 2. Yep. Cosine and sine of pi over 4 are the same thing. And then plus 2 plus 2 plus, okay, now we have sine of 3 theta. So sine of 3 pi over 4. Sine of pi over 4 we already said was root 2 over 2. We're in the second quadrant there. So that's going to be the positive, right? It's going to be positive in that quadrant. So we're going to get plus just square root of 2 over 2 times square root of 2 over 2 all over. And we're going to have 3, and we've already calculated all these, so we'll just fill it in. So 3 cosine 3 theta is negative 3 square root of 2 over 2 times cosine theta, which is square root of 2 over 2, minus 2 plus square root of 2 over 2 times sine theta, which is square root of 2 over 2. Okay, and from here, I mean, you've basically done, the hard part of taking the derivative. We're just going to simplify, right? We'll get, let's see, it's going to be negative 2 over 4, so negative 3 halves, right? Because we have 2 over 4, 1 half, plus root 2 plus root 2 over 2 times root 2 over 2 is 1 half over, and this is also negative 3 halves, minus 2 root 2 plus, or minus again, minus 1 half, which, I'll just go ahead and put it over here. We get, let's see, negative 1 plus root 2 over negative 3 halves minus 1 half is negative 2, or sorry, this is there should be a plus 2 on there, or no, this is negative 2 minus root 2. Okay, great. That was a lot, but hopefully you can still grasp onto it a little bit. So go ahead and take a break. I'll give you 10 minutes. We'll come back at 5:05 for a much shorter section. We're just going to do areas and arc length